Okay, so I know this is busy. This is busy slide. What I threw this slide for you guys to understand that every power system starts with a transformer. Every power system starts with a utility service transformer. The utility service transformer will decide how much juice you can get into your building and what's the voltage that your building is going to be burning at, right? Is it 28120, 24120? Is it 48277? So the utilities give you two services. The lucky ones of you will deal with two of them. The unlucky ones will spend 90% of your time dealing with only one type of service. The first, the two types that they offer, the utilities guys offer you is service. It's called 600 volt or less. Service that's 600 volt or less. That will cover 90% of the customers that you're going to be dealing with. They're going to be taking service at 600 volt or less. At 600 volt or less. So that's the first thing I want you guys to understand. 600 volt or less services. Cool? Everybody knows the voltage limitation. And let me just jump quick to the second service, set of service. They call them primary service, high voltage service, more than 1200 voltage, more than 600 volt. So there's 600 volt or less and more than 600 voltage. So let's just talk a little bit about the 600 volt or less. You're going to encounter this one 90% of the time. 90% of the time, you're going to have any one of these five systems that you're going to encounter. Five systems in the US that we offer. Internationally, we offer very similar systems. I'll highlight this one. The first system that we talked about, guys, is power system number one. They get you 70 to 100 volt from phase A and the ground, and from the other side, you get 241 volt system. This is used for single phase and residential only, up to 800 amp plus light commercial. Everybody can see, read my handwriting. So this system, single phase only, residential plus light commercial, typically, and up to typically 800 amp services. Cool? Thumbs up? Typically, don't hold me accountable to the amps. And the voltage that you get is 24120. And we designed a project apartment building. Last project was what? 24120. Started with this power system, which is transformer 24120. The primary voltage, can you guys see what the primary voltage, the pole, that little transformer, pole mounted transformer that Excel can give you? The primary typically is 70 to 100 volt to ground. Any question, guys, about system number one? Know where we use it typically, right? Let's go to system number two. System number two is, I'm putting the voltages, the typical voltages that Excel will give you, or other utilities, 13,800 volt on the primary side. On the secondary side, you have a 24120 three-phase. This system is a three-phase system. Can you guys see the difference between this is single-phase system, this three-phase 24120 three-phase system? Center tapped. They take one gut of the transformer tied to the ground. Can you guys see where the ground is here? The ground is here. The ground on the top one is right in here. I don't know if you can see where the ground here, and also the ground is this side. This is how you get the ground on the top one. Number two, you only have one ground, which is coming from that little point. That's where you get your 24123 phase system. Where would you use this? Only 10% of that, when 10% or less is a single phase load. Lift stations, well houses. You have a house full of pumps that pump the water to the city of Bloomington, city of Minneapolis, right? All the pumps are running at 243 phase. The only thing that you need single phase is what? Just a couple of lights and a couple of receptacles. That's a typical system for this. So they take a delta, ground one center of it, center tabbed delta here, and can you guys see that? And this will be your neutral. That will be your neutral right in here. And where do we use it? Three phase. Again, if your load is less 10% or less is less than is single phase. Typically, commercial plus light industrial application, 1600 amps is up to, of course, 1600 amps. That's a typical application. Not commonly used though. Number two is not commonly used. Number two is not commonly used. Any question, guys, about system number two? That's a transformer or transformers that can be banked together to give you a 24123 phase system. Any comments, any questions about this system? Any comments, any questions? Does it make sense? Okay, moving to the, so system 1, system 2, moving to system 3. System 3 is same thing, 13.8. This is, by the way, 13.8 kilovolt here. 13.8, 13,800 volt. It's a delta on the primary. On the secondary side, it's 28120. Can you guys see where the neutral, the grounding here, and they have your neutral, 3-phase, 28120. Isn't that the system? Number 3 is the system that you guys are doing right now with me. That's exactly the system for commercial. Very typical system, commonly used. It's a 3-phase. Where would we use it? Recommendation. Again, recommendation. Please don't hold me accountable. Recommendation, if the square foot of the building, Kerry, my friend, is 15,000 or less, 15,000 or less, typically they give it 3-phase, 15,000 or less. Typically we give it a 28120 3-phase system. Typical. Cool? That's good application for it. Why can't I use a 24120? You will be a fool if you have a 3-phase system and you're building and use a single-phase system. If you have a 3-phase system and you have a commercial building, the Excel will give you 99% of the time 3-phase service. It's easier, better for the utilities. Everybody knows utilities love 3-phase system. It balances the loads much better. So if there's a 3-phase commercial, especially commercial industrial, they love to give you 3-phase system if there's a 3-phase system in your area. Sometimes they don't have it. Okay, so here's what the most typical. Where would you use it? Residential, apartment. This is risers, high risers apartment, right? Residential high risers. Commercial and light industrial. And up to, we can get them up to 4,000 amp services. Up to 4,000 amp services. Can I have thumbs up, Chad? We fully understand how this system works. This is one of the most common systems. System 3 is one of the most common system for commercial and light industrial and high-level residential apartments. So for high-risers apartment, for commercial and light industrial. When I say light industrial, guys, I don't mean light. Light meaning light industrial, meaning it's not like chemical manufacturing plant. It's a shop, shops and all this good stuff. That's what light, as in light loads on it. Cool? So 4,000 amp. Then we move to the second most common system. Same thing. You have, this is the system number 4. The voltage on the primary for this system, guys, is the same voltages. Let me use it right here. It's 13.8 on the primary, 13.8 kV on the primary. On the secondary, it's 480-277. It's a 3-phase. Where would you use this? If it's a square foot of the building, typically is more than, if your square foot is more than 15,000, that's a typical application for it, 480-277. Heavy commercial and industrial. Heavy commercial and industrial, that's the application. Heavy commercial, malls, strip malls, closed malls, and industrial, bigger shops, bigger factories. They take 480-277 for up to 4,000 amp. Can I have thumbs up, Chad? We understand that distribution system. Okay, so that's your distribution system. The last distributions, I highlighted these in red for a reason. These highlighted in red. These are between these two voltages. You will cover 90% of the systems that you're going to be working on in your career between 2.8 and 480. Cool. The last system that we barely use, I think it's used in certain areas in the US, a lot in Canada, is this system, 13.8 on the primary transformer. On the secondary side, they give you 600 volt and 347 volt to ground. 600, 347 to ground. That's a Canadian system. It's used in certain parts of the country. Where a good application for this? Very large industrial plants. The higher the voltage, guys, the more power you can pump through your building, right? So you raise the power higher, you can start feeding bigger plants. If you keep raising it, starting to feed, instead of feeding plants, you can start feeding cities and towns and states. Does that make sense? The more and more higher you go in the transmission line. Any question about this very commonly used systems in the US? Any question?
Up to 4,000 amps.
Yep, all of them up to 4,000 amp. Yep. These are 3, 4, 5 are 3, 4, and 5. They all go up to 4,000 amp.
2, 3, and 4. The primary is going to be always 13.8.
99% of the time. There's another primary that they use if you guys want to throw it. The utility is moving away from it. It's called 4160, 4.16 kV. That's another common voltage that they use. A lot of utilities moving away from it because it's lower voltage in their mind. So 13.8 is typically what you're going to be encountering. These are the typical. Yes, sir?
Do 4,000 amps, 600 watts, or 600 volts, only at 13.8.
This is a transformer. The primary voltage is going to be completely different from the secondary voltage. You know, primary and secondary are completely different. The primary voltage here is owned and operated by Excel and the electrical utility in your area. The secondary is owned and operated by you, right? Any question, guys, about the services? The service is 600 volt, low voltage services, 600 volt or less. Cool? So between 3 and 4, gentlemen, you are going to be, between the 3 and 4 here, you're going to be, let me just verify, this will be my 3 here. The voltage here is also 13.8 kV. Between 3 and 4, this one and this one, you're going to cover 90% of your systems, commercial industrial systems. Can you guys see that these are Y, this is a delta. There's also a system that use delta, I didn't put it here. Also, a delta application is similar to 2, guys. If anybody see delta, that will be 240 only, delta, and that was similar to number 2, exactly the same, similar to number 2. Any question about these voltage systems? That's your start point, the power start point. Now, if you're lucky enough, if you are one of the lucky ones, you will be getting a high voltage service, like 3M, Mayo Clinic is a good example. Gerdau or North Star Steel is a good example of getting a 3-phase service. All these big manufacturing plants, the petroleum plants, they get the service, guys, at higher than 600 volt. Okay, so where would you use the service higher than 600 volt? As I said, they have 3M, U of M, Mayo Clinic, examples of places where they get higher than 600 volt. And you can think of that caliber type, all the petroleum manufacturing plants, very, very large industrial plants. They take higher than 600 volt. The criteria for these are typically campuses. You go to the 3M, it's the campus of 3M is bigger than towns, right? The buildings and all stuff, the area that they cover, it's like a town. So when you're looking at a plant that's like a town, do you really want to give it 480 to distribute the power? You're going to give it higher. It's you start treating these campuses like towns, right? Same thing, University of Minnesota, multiple buildings. It's bigger than small towns, the U of M. So they start multiple buildings, one service, one owner for the most part, like the U of M, 3M, they own that area, and you provide a service higher than 600 volt. Everybody knows these are justification. Where would I use a service higher than 600 volt? Campuses, smaller town, almost small town. Can I have thumbs up, Chad? We understand that? You guys probably, you will encounter this one if you're lucky, 10% of your career. Most of the stuff you're going to be dealing with this than 600 volt. Okay. We've done that. I've done that one for Mayo Clinic for building. They brought a 13A to the 13th floor. They have a substation in the 13th floor, and they fed everything down from the 13th floor up to the 32th floor, I believe, or 26th floor, all the way with 480. But up to the 13th floor, you brought 13A to a substation inside the building. So it's big, really cool stuff inside the building.
Stadiums too, like
Stadiums, I don't know how the power of the stadium, but it's a good candidate stadiums for that 13.8. Depends on the power. I don't know if they do 13.8 in prisons, but is it 13.8? Okay. I guess prisons could be as big as almost a canvas, right? Okay, but you can see the idea. It's a big customers. Okay. Here's how they get you the service, guys, then. You get a service. This is how they do it. They get you a service at 69 kVA. The line that's coming to your building will be 69 kV, meaning 69,000 volt, up to 115,000 volt, the primary delta. Then they give you another delta here, delta. From the secondary, that's what you're going to get here to your building. They can go 2.2400
or 4.17, 13.2, 13.8. These are the typical voltages that they burn your equipment at. Now remember, these are the voltages they're going to make a switch gear for. That's inside your building. 13.8 switch gear, 2000 amp switch gear, that's a high voltage switch gears. So the Excel will give you this voltage on the primary side. On the secondary side, right, this is the primary. On the secondary side, you'll get any of these voltages. The most common voltage is this one, 13.8, very common. So you have 13.8 going through your campus and feeding multiple buildings, from building to building to building, feed all these, loads. When they come with the 13.8, here's the 13.8 landing in the circuit in the switch gear. From the switch gear, they take multiple 1, 2, 3, 4, 5, 13.8, or they call them 15 kV draw out circuit breaker that feeds 5 buildings here. Every building will have its own feeder, and all of them are 13.8. What's the beauty of this? Voltage drop almost zero. No voltage drop to talk about, right? Higher voltage, great for voltage drop. No losses, no voltage drop. Efficient system. What's the drawback, Andrew, my friend? Is dangerous. Now that if 480 can kill you, this can evaporate you, literally. If you get a short circuit at 13.8, they wouldn't find you to bury you. At 480, they will find you. You will have a proper burial, but at 480, at 13.8 switch gear arc flash inside it, you might not be found. Literally, that's how dangerous these voltages are. So that's the drawback. Now you're putting a system like this right inside the building. That's why they have locked doors, guys. Electrical doors, locked door, high voltage, don't enter, and all these warning and all this good stuff, so they don't kill people. Any question about high voltage service? Can I have thumbs up, Chad? We understand the low voltage, high voltage service. You cannot understand. You cannot be a good electrical designer without understanding these services, guys. You cannot. So who's going to ask for the service? Who decide which service to pick? The design engineer, yourself. If I'm doing a project for 3M, I will ask Excel for a 13.8 service, right? Most of the stuff, guys, have been already decided before. The people before us decided that these customers 13.8. If I go to Excel right now and I tell them Dunwoody would like to get 13.8 service, they'll laugh at me, because Excel and the power companies know who are the big players in their area, the big consumers, and when you go to them with big chunk of load, they will give you a 13.8 service. They have to decide on 13.8. Same thing, 482.77. Which one decide on the 482.77? We decide. Because Excel give you a primary voltage, and what type of transformer do you want to do there? You, and as an engineer with Excel, you decide, I'm going to have 480. So they put a 480 transformer. I'm going to have a 2.8. Then they put a 2.8 transformer for you. Does that make sense? Between you and Excel or the electrical utilities. But the higher than 600 volt, it's always almost the utility have to agree on that. They have the bigger C on the higher than voltage. Okay. Having said that, the two slides that I gave you guys, for one reason, to justify what I'm going to be calculating here. That's all. Why am I going to put you through the torture of calculating things about these transformers? Why am I torturing you, gentlemen? Because the transformer is the start point for the power system. Any power system have to start with a transformer. Cool? Have I convinced you guys that these are the start points? Now we're going to go do calculation for this start point. Cool? Can I have thumbs up, Chad? So that's the start point. Now, I have two examples, I believe, here. Remember, this is the power system. Now, we talked to Excel, and we decided for our building, right, the building that you guys have, we need a transformer of 100 kVA, right? Our transformer was 225, if you remember. This is 100 kVA transformer, and I decided in conjunction with Excel that my building is going to take 2.8, 120, three-phase system, Y grounded, and the transformer is 100 kVA. Well, actually, this is an indoor transformer. I bet. This 482.77. These are typically they use this one, guys, to get you 2.8, 120, right? So say I have like Dunwoody. We are Dunwoody here. With our service is 482.77. So how am I going to power these suckers here? How do you power these? When you have 48277. Any suggestions? Transformer. So that's where this transformer comes handy. They take the 480, they put it in a delta on the primary, because I care less about the neutral on the primary than transformer, and they feed it Y on the secondary, and they get you the 28120. So can you guys think of this? These are called receptacle and lighting transformers almost, or low voltage transformers, because they get you a low voltage system. Okay, one more time. I have a 480 delta on the primary, and I have on the secondary side, I have a 28123 phase. I have on bonding. Here's my grounding electrode conductor number 5. Number 6 is the main bonding jumper right at the transformer, because I own and operate this transformer. This is called separated drive system. I own and operate it. My transformer is 100 kVA. And I want to size the following. I want to size number 1, the primary feeder. Number 2, the primary fuse. Number 3, the secondary feeder. Number 4, the secondary circuit breaker or fuse. Number 5 is the grounding electrode conductor. Number 6 is the main bonding jumper. Any question about what we're supposed to size? Is it clear? They're all 3-phase. Everything is 3-phase. Yep. You see phase A, phase B, phase C, and A, B, C. Everything is 3-phase. Cool. Can I have thumbs up? We understand what type of transformer are we dealing with here? We're dealing a 480 on one side, 28120. Where would I use a transformer like this? To feed a receptacle pan from a 480 system. You guys are going to be doing it not in this project, next project. You get it now, you're good to go. You didn't get it now, you have another chance to get it next project. Okay, why do I care about sizing the feeders and the fuses? What do they call you? You're electrical designers. Who's going to be sizing the feeders better than you? Okay, why do I care about this power? Because that's my source of power, right? That power system started right here at the transformer. Okay, so let's go guys ahead and size these. Before I leave, I want you to understand we're sizing the feeder primary conductor, the feeder primary fuses, the feeder secondary conductors, the feeder secondary fuses or circuit breakers, the grounding electrode conductor to ground the neutral of the transformer, as well as the main bonding jumper to bond the neutral of the transformer to the grounding electrode system. That's required for so-called separated drive system. Separated drive system. Any comments, any questions? Now imagine if I have to draw this and you guys have to sit there and draw that, all this stuff will take us a while, huh? That's why I print these and give it in front of you. Okay, shall we go ahead and size these boys? Shall we? All right, let's go ahead in the first one. Primary feeder. You guys have it in front of you. So let's go to, I have my, so this is my primary feeder conductors. Where am I here? Okay, right in. That's interesting, huh? How that goes. Okay, so I have my primary feeder. The first thing you need to size, when we size conductor, do we size conductor based on voltages or amps? Have you ever gone to Excel and to Home Depot and bought a conductor that can carry 233 volt? Typically, we size them based on amps. The installation have to be rated for voltage, 600 volt or less, or more than 600 volt, but the sizing is based on amps. So I need to calculate the amps. I will remind you the amount of power that this transformer can generate on the primary and the secondary, not generate, transfer, is 100 kW. So if you take the primary, let's use, I'm going to use red here. So if you take 100 kVA, not kW, divided by 1.73, any suggestion why 1.73? 3-phase, thank you. And what's the voltage on the primary side? The primary, 480. Now we're calculating I primary of the transformer. Anybody can come up with other than 120? 120 amp. So that's my current, 120 amp. Any question, guys? Any comments? 120 amps. 120 amps. Okay. Now, assuming, now I will size, this is the full load amp on the primary side. I'm going to assume it's going to be a continuous load. So what do you do if it's going to be a continuous load? Anybody suggest 1.25? Now that's an assumption, a good assumption though. I'm assuming I'm going to have a continuous load, and that's based on 215.2A1. Then you can get 1.25 multiplied by 120. That will get you what? That will get you 150, right? And if you go to 310.15 B16 under 75-degree column, how many conductors and what size? Anybody? So you're going to end up with 3 conductors. Number 1 aught, A, W, G, T, H, H, N. THH, why THHN? This is a transformer inside my building, right? So 3 conductors, number 1 aught. 3 conductors. Why 3 conductors? 3 phase. Where's the neutral on the primary side? None. Do I care about the neutral? No, I'm not carrying a neutral, right? Any comments, any questions? Any comments, any questions? Okay, does that make sense, guys? Is that easy, hard? No, yes? Shall we go to primary overcap protection device? Now, we size the conductor. Let's size the overcap protection device. For overcap protection device, guys, for transformer, I would like you to go to table 450.3b, which I have it here. Okay, so if you look at 450.3b, you guys have a picture of it. If you have not highlighted this table, it's about time to do so. Here's how the table looks like. This is overcap protection device for transformers. The primary, both the primary and the secondary, can you guys see that? The primary and the secondary are less than 600 volts. Is this transformer primary and secondary less than 600 volts? Let's go back again and look at it. Look at the primary voltage and the secondary, 480 and 208. Are they less than 600 volts? Yep, so this is the right table. If one of them is more than 600 volts, can you use this table? No. Okay, so here's this table, so 600 volts or less. Then they split it if the current primary is more than 9 amps, and if the current secondary is more than 9 amps. Okay, am I more than 9 amps on the primary? Yep, so what's my multiplier? 125. Can you guys see note number 1? If you read note number 1, what does it say right here? Highlight it. It says if you don't hit the standard, what do? Go up. Thank you. Go up. Let's go back into the secondary side. Secondary. Am I current more than 600, more than 9 amps? Yeah. You can use. You have 2 options. If you don't have to have a secondary. You don't have to have a secondary. If you don't have a secondary, then you have to multiply by 1.25. If you have a secondary, which is a good idea to do, then your multiplier will be 125. If you're not a standard, I don't know if you guys can see that, you can go up. But on the primary side, you can multiply by 2.5 times the full load current to the primary, but can you go up here on the secondary? No. So which one is your default? You're going to default to the second row. The second row is your default, not the first one. Second row. Your primary is going to be multiplied by 1.25. Your secondary, your primary will be multiplied by 2.5. Can you have a thumbs up, Chad, for this? Cool. Please highlight this table. Here's my primary. Here's my secondary. Find the full load current, multiplied by 1.25 because of this, by 2.5 because of this. Now, Jeff, if this is not a standard, I have to go down here because they don't allow me to go up unless I custom design a fuse and pay an arm and leg. Here, they say note number 1, if you don't hit the standard, what do? Go up. Can I have thumbs up? We understand this one, Chad? Because if you don't understand this one, you don't understand transformers. Okay, everybody understand this table? Highlight this table in the code. Okay. So let's go back and size it then. So I have my full load amp is 100. My full load amp, guys, is 120. It's the primary. So what do you multiply? What was the multiplier for the primary? 2.5. Thank you. 2.5 equal. That will give you 300 amp even. Okay. If you don't know that 300 amp is a typical fuse or circuit breaker, typical fuse circuit breaker, you're going to take it to 240.6, right? And you know that this is a standard. 300 amp is a standard fuse. So what size of fuse am I going to put on the secondary maximum? 300 amp. Now, Andrew, you go work for a company and they say your friend Chad 30 is dumber than a rock and we're going to put 250. Is this okay? To put not like he's dumber than a rock. Is it okay to put 250? Yes, no problem. You can. Maximum. The overcomputation device is always a maximum. Can I go from 300 to 250? Yes. Lower, yes. Higher, no. Why? What's the disadvantage of going lower? If you go lower, you're taking a risk of every time you start, when your transformer starts, you're tripping or burning the fuses. That's the risk that you take. Now, if you're a company like Parson and Egan and all these big boys, and you have done tons of them, and you know for a fact this type of transformer work with this type of fuse based on the manufacturer recommendation, and Chad said 300, but I know I can put 200 and work with it for 15 projects that we've done. Can I put 200 there? Yes, no problem. The max is a 300. If you're a designer like yourself, have no idea what type of transformer you're dealing with, to cover your butt, what do? You go to what the code says. So when they send Gary Ryman to review your design and goes over the code calculation, if it burns or if it doesn't start and you have to pay for it, you say, well, at least I followed the code. Your chances of winning a case is higher. Doesn't mean you're going to win it, but your chances are higher. Any question, guys, about this? Yes, sir.
So then for the primary OCPD, if you were on a standard, you're gonna go to the lowest or the least motor size? Because that's the maximum.
This is the max.
So if you weren't on a standard, you're gonna go to the next motor size?
No, the standard says go up.
So
Yeah, see, if you look at the table, not says, it says you're allowed to go up. Now, can I go down? Anytime. That's why we go to work for a lot of firms, guys. Students say, Chad, you can, when I went to the work, they size it lower. Yeah, they size it lower. Don't worry about that.
For the primary?
This is the primary.
Oh yeah, you drew it down arrow on that other sheet. I think that's why you might be confused, because I thought down too, see, down arrow.
Hey, I'm sorry, you go down. You're right. You go down. On the primary side, you're right. On the primary, you go down. Because there's no nut number one here. I was looking here. You go down because we're using this, right? You see any nut number one here? You go down. Did I say you go up on here? If it's not a standard, then you have to go down. Let me just put it down here. Thank you. Okay, so you go down if it's not standard. Any question, guys, about this? Any question about this? You go down. If you, that's why, guys, when I say highlight the table, because you get confused which time you go up and down, go to the table. Always the table will tell you. Always look at the table. Okay, so we find the primary stuff. Let's go to the secondary stuff. I want to remind you before we go to the secondary, my friends, on the secondary side, here's my multiplier, right? Because my amps are more than 9 amps. I hope you have more than 9 amps. Because they're divided with current less than, this is for I, less than 9 amps, this column here. And this column is for I, more than 9 amps. We definitely going to have more than 9 amps. So which column are you going to use? This column. And since the default is the second row, my multiplier is 1.25. In this case, Jeff, I will go up because of nut number one. If you read it down here, it says you can go up. Thumbs up, Chad. Let's go do it. Okay, so secondary current. How do you find the secondary current of a transformer? Any idea? What's the kVA of the transformer? 100 kVA. Divided by 1.73, multiplied by, what's the secondary voltage of the transformer? 208. Why 208? Because we're on the secondary side of the transformer. You can't believe how many people, guys, they go and put 480 here. Always remember, especially Aaron, my friend, you did do transformers, right, with us? With transformers, they have 2 voltages. When we go to Revit, that's a good point to pick point on Revit. When you guys go to Revit and you start circuiting to the transformer, you have to understand when you circuit to the transformer is going to have 2 distribution systems. One based on 480 and one based on 208. Okay, you're going to see when we start circuiting, you go pick up the transformer, you're going to circuit it to the panel, say, Chad, well, it's not circuiting. Well, because you didn't assign a 480 to it on the primary side. If you want to circuit to it, it has to be assigned to 8. Okay, so what's the answer? Too much talk, Chad. 278 amps. Anybody came up with something different? 278 amps. Okay, so that's the first step that you need to do. The second step, guys, is you're going to take the same thing, assuming it's continuous, 1.25 multiplied by 278, good assumption, and that will get me 348 amps. 348 amps. Cool? 348 amps. And then you take the step number 3 is take your 348 amps, take it to 310 of 15 B16 on the 75-degree column. That will get me how many? 3 conductors, number 500 KC and M THHN. What happened to the neutral, Chad? I'm going to derate the neutral. Right? I want to derate the neutral. You go higher than 200 amps, always apply the rating for the neutral. Always. Am I higher than 200 amps? Yep, derate the neutral. Okay. So here's my 3 conductors, the 3-phase. These are the 3-phase ones. What's insulation THHN? Why THHN? We're inside the building. We're inside the building. Can I do the neutral now? Let's go to the neutral. The neutral, guys, now because I don't know what the neutral load, that's Chad. I don't know what the neutral load is on this transformer. I always use the load on the phase and derate it based on the following. So here's my neutral on the phase. We calculated this one is 348 amps, right? Cool. So now I want to remind you guys, if you go to 220.61B2, if you go there, it tells you anything higher than 200 amp, chub it by 70%. Do you guys remember that? We used it before. So I have 340. So here's what I'm going to do. Then I'm going to take the 348 amps, the first 200 amp, do not mess with them. Anything that higher than 100 amp, which is basically 384. Nope. What is this, Chad? Why am I? Did anybody write another 8 here? Brian, did you write the other 8? 348. It's a lot of 8s, man. 348. So same thing here. You take the 348 minus 200, and you have to multiply this one by what? 0.7. Okay, so if you do the math on this, and make sure you add them up, I'm going to put add here. You add them up, right, like we've done. You're going to end up with 304. You're going to end up with 304 amps. 304 amps. Okay, 304 amps, cool. Now the last thing is to take the 304 amps. I'm going to make it here. I don't have, should have enough room here. Right here. I take the 304, take it to table 310.15B16. This is a table, 75-degree column. One conductor number. Anybody came up with one conductor number 350? 350 KCM THHN. One conductor. Cool? So you take the 304 and you size one conductor. So can you guys see we went from 500 to 350. Typically, Jeff, even if you don't do the calculation, when we size the neutral, we size it 2 to 3 steps below the phase. Typical rule of thumb. That's one justification. So I can pull a smaller neutral. Because I have no idea what's going to be on this transformer. Do you? It's tied to a panel. I have no clue what's going to be on it. Okay, any question guys about that? So that's the, so how many conductors? 4 conductors, 3 of them 500 kcm and 1 350 on the secondary side. Let's go to the overcomputation device on the secondary side. So overcomputation device on the secondary side, guys. Step number one is, remember that multiplier, 1.25. Everybody got that one? From table 450.3b. Multiply this one by 278. What do you get? You get 348 amps. We've just done that. Step number two is you take the 348, take it to our notoriously famous non-adjustable circuit breaker list, 240.6. Did you guys hear me saying non-adjustable? Because if you have adjustable, it changes the whole equation. That's next project. So these are non-adjustable. You can adjust them. Adjust the pickup anyway. What's the next standard? 350 amp. And this is where you go up. Why do we go up, guys? Because note number one, if you guys remember, it says, Chad, if it's not a standard, go up. Right, Aaron? Did it say, Chad, if it's not a standard, go up? Any question, guys, about this? Any question? Yes, sir.
Question. For number 3, step 1, I guess you'd say.
Number 3, step 1 here.
You're dividing it by 1.7.
Where did the voltage go? Why did you guys, did anybody steal my voltage here? 208, thank you.
Yeah, that's
Very
not,
good.
but 1.73 is at like square root of 3.
Yes.
Okay. Well, I mean, I'm not trying to like
No.
screw with you, but like it's 1.736. Is the-
1.726, isn't it?
1.736.
32.
Is it
32.
0.732?
32. So we
Okay,
dropped
I'm
the
about
2.
to say like you're on the wrong. Get it wrong.
No, don't worry about it. 1.73 is good enough. That's excellent. I think it's 1.732.
And that comes out to about 360. I don't even know.
Yeah. Just slightly. We can deal with that.
I was making sure you hadn't rounded it wrong. It's like
No,
it's like
1.7.
giving it this.
Good point, though.
Okay.
Any question, guys, about this busy slide? Cool. Let me finish this example. I'll give you a break here. Let me just finish the second two. Next, since you guys are going to be paid $20 an hour when you graduate from here at least, right? Isn't that what you're going to be paid? And I hope so. And they want you to size the grounding electrode conductor for separately derived system. Now, what the heck is a separately derived system, Chad? Separately derived system, let me just go back into my transformer. Can you guys see this? This is called the separately derived system. Why? Is there any connection between the phases and the neutral on the primary to the phases and the neutral on the secondary? Any physical connection? Do you see any? You see phase A tied to phase A on this side? Is there any connection between the primary phases and neutral and the secondary phases and neutral, if any? Is there any? None, right? That's called separately derived system. Can I have thumbs up, Chad? Separately derived system. There is no connection between the phase conductors on the primary side and the phase conductor on the secondary side. Completely isolation. So that's your phase. Okay, so let's go there. All right, so we have so we need to size the grounding electrode conductor. The grounding electrode conductor, if you guys remember, we size it based on the phases. So I have 500 kcm. Go take this one to 250.66, and that will get me a healthy one conductor number 1 aught. One conductor number 1 aught. This could be bare. This could be THHN, or it could be covered. Right? Any one of the following. Typically covered in engineered project, you will have a THHN green conductor going all the way, or a black conductor with a tape, green tape going on it. So you can use a black conductor gas for a grounding electrode conductor as long as you strip it a couple of inches, so you can show it's actually uninsulated, or you can put the tape on it. Typically what they do. Okay, system bonding jumper. Everybody knows where the system bonding jumper, that's where you take the neutral bonding to the grounding bar in the panel or the switchgear. Same calculation, system bonding jumper, they call him system bonding jumper, not main bonding jumper. Main bonding jumper at the service, system bonding jumper at the separately derived system. 250.30A 1 and 3 and 250 plus 66 will tell you exactly what I'm going to tell you right now. Which is basically you take the 500 kcm, 250 plus 66, and you get your one conductor, number 1 at AWG THHN, bare or covered. Any of these options. And now this is the rule, right? Right underneath it here, this is that check that we have been doing with me guys all the time. If the conductor size is more than 1100 kcm copper, then multiply 12.5%, take 12.5% of the phase conductor. You guys remember that? Now, is my conductor more than 1100 kcm? No. So do I need to go to step 2? No. Why did I put step 2 for you? Reminder. I always use copper, guys, but if it's aluminum, if you go there, I think 1700 for aluminum. 1700 for copper, it's 1100. So if I'm mean, what do I do in the test? I put aluminum. Right? Brian, do I look like a mean guy? Yeah. Oops. I shouldn't have asked. That's the problem when you ask you. You get what you get. Yeah. Any question guys about this? Any question about this transformer? Okay, let's take 5 minutes and let's jump into another transformer. Listen, we're going to do the same calculation for a couple of transformers basically until you guys get it. So let's take 5 minutes.
So your GEC and your bonding number is going to be the same?
Up to, let's go and continue with a nice transformer dear to my heart, and I'm sure it's dear to Brian's heart as well, because he works for Excel Energy. So,
You mean he sleeps for Excel Energy?
okay, here's a typical transformer. That's what you typically guys have in a building. We have a 4160, it's called 4160, they call it 4160, 4160 volt coming on the primary side delta. On the secondary side, I have a Y. Why do you think almost always we get a Y on the secondary? Anybody can guess why we always like the secondary to be a Y? Because you get 2 voltages, right? Yeah, that's the, and yeah, but yes, dangerous for equipment, absolutely. Number one, a grounded system is more, it's a better system than ungrounded system in terms of equipment, doesn't burn equipment on spikes, and number one. And number two, we get 2 voltages, right? You get 2 levels of voltages that you can burn at. Okay, so let me go over what we have here. We have a transformer delta Y, primary provided by Excel 4160. Secondary is coming to my building. My voltage though is 480/277. And the transformer that we ordered from Excel and they dropped it right by our building is 1500 kVA. So 1.5 megavolt, they call it. 1.5 MVA or 1500 kVA. Okay? So what's my job and yours? My job and yours is to first size the feeder, the primary feeder. Second, the primary fuse. Third, the secondary feeder, the secondary fuse, the grounding electrode conductor, and the main bonding jumper. The main bonding jumper. So exactly what we did for the other, same thing like we did for the first transformer, guys. Typical, when you have a transformer, these are what they ask you for. And then you can add the conduits on both sides. That's easy, right? If you know the conductors, you can size the conduits. Cool? Any question, guys, about this system? Now, can somebody tell me the secondary is the secondary higher than 600 volt? Secondary here. No. So I have a primary higher than 600 volt, secondary less than 600 volt. Okay. So let's go size the feeder. The most important thing when we size the feeder, first find the amps. So let's go find the amps. The primary amps, my friends, you take the 1500 K, V, and A divided by 1.73 times. What's the voltage on the primary? On the primary, 4160, right? The primary, we're doing primary first. Number one is primary. Everybody knows that number one is primary.
1500 kVA or 150 kVA?
1500 kVA.
So 1,500,000
Yes.
volts.
Yes. Big boy. Big boy, right? I know a lot of people say, oh, wow, that big. You can get 20 meg, guys, and 30 meg and 40 meg transformers. Okay? So you're right, it's a big boy. Yeah, so I want to remind you, Adam, that you have to multiply by 1,000 too here. That's mistake number one. People forget the K, cache the K. Remember that caching the K? Cache the K when you do the calculation. So when you do the math, you end up with 260 amps. Can you guys see how, can anybody see how a big transformer have a very small amount of current because the voltage is so high? Can you guys see the advantage of having a high voltage? Okay, so 260. Now, this is step number one that you have to do. Step number two,
208 on the.
I got 208, supposed to be 480.
you know what? You're right. I think I just grabbed the wrong number here. It's a 208. 208, I just grabbed it from after I multiplied by 125. You're absolutely right. So that's 208. Then you take the 208, multiply it by 1.25, assuming it's going to be a continuous load in that transformer. Okay? And now this is where I want you to wake up, guys. 1.25 times, oh, I'm sorry, here, I think we have, one second. We have, we have a 208 amps here, right?
Yep.
And we have,
That'll be 260.
I'm just ahead of myself. This is going to be your 260 amp, absolutely. Are we clear, you guys? We got the 208, multiplied by 1.25, get you 260, cool. Clarify it. And then you have the 260 amp. Then you take the 260 amps. Makes sense now?
Yep.
Okay, sorry for that. So the 208 multiplied by 1.25 times 208 gets you 260. Now, I want to remind you guys, look at the voltage. The voltage is 4160. Can we go to 310.15B16? No. We can't go to 310.15B16. Why can't we go to 310.15B16? Because 310.15B16 is only for cables 2000 volt or less. Is the system 2000 volt or less? No. So now you're going to go to a completely different table. Okay, so before I go there, I'm going to flash the couple of tables for you and make sure you guys have them in the code. Okay, the table that there's so many tables that you can go for higher than 600 volt. The most common table is this one, the 310.60C77. Okay, 310.60C77. Unless they tell you otherwise, that's your default. That's your default. Everybody can see it, 310.60C77. This table, anybody have ever seen this table? Have you guys ever seen this table? That's brand new to you. Okay, let's talk a little bit about it. The first thing, the ampacity of 3 single insulated copper conductors. I'm an engineer, I'm in the copper. So this is for single conductor in an underground electrical ducts, 3 conductors per electrical ducts based on the ambient air temperature of this, electrical duct arrangement of this, and 100% load factor, and the resistivity of 90, and conductor temperature of 90. Okay, so that's basically the table. The way you use this table, so these are 3 conductors in 1 conduit, underground ducts. So let me show you how it looks like in here. This is the arrangement that they're referring to you to. These are for high voltage. Here's the underground duct, an underground duct. Inside it, you see that dot here? That dot represents 3 conductors. 3 conductors that I'm going to size. Phase A, phase B, phase C. High voltage. Okay? Why did I pick detail 1, not detail 2, not detail 3, not detail 4? Here, I can have 3 circuits. Here, I can have 6 circuits. I can have 3 circuit this way, 6 circuit this way. So these are direct buried cables. There's so many configuration of putting medium voltage underground. The same thing for low voltage, by the way. This configuration, the same thing for low voltage. We do the same thing for low voltage. One more time. Since most of you guys are going to be dealing with only one feeder, higher than 600 volt, so your detail number 1 will be good enough for you. So you put a duct, PVC duct or any type of duct, encase it with concrete and bury it under, I think it's 24 inches of concrete. You bury it with this amount of, 11.5 by 11.5 inch concrete block in the ground and bury it with 24 inches of dirt. That will be your duct. Can I have thumbs up, Chad? We understand what you're doing, going underground in the concrete. Why do you think we do this? High. Yes, high voltage. Do you want to cut into that cable, really? Okay, so before we leave, can you guys understand that the dot, can you understand this dot? Can you guys understand that this dot could be 1 cable or 3 cables? Each one of these dots, in my case here, it's 3 cables. If I need 3 circuits, this could be 3 cables, single conductor cable, 1 circuit. This is circuit 1, 2, 3. So if I'm paralleling conductors, if I'm paralleling circuit, this will be 3 circuits. That will be my option. If I need to parallel 6 circuits, that will be my option. Or this, depending on the configuration, how you're going to lay them out. Cool. If I want to bury it underground, no cable, no conduits, here's your distances, detail 5. So typically for medium voltage, guys, we put them in a concrete. So detail 1 is the default. Can I get thumbs up for detail 1? Okay, now let's go back and see what the heck is why is this important. When you get to this table, can you guys see right here, detail 1? Everybody can see that detail 1 here. And right here, detail 2. Everybody can see the detail 1 and detail 2, right? So why did I pick up detail 1? The default. Unless you want to do it otherwise, you will default to detail 1. 1 circuit, 3 conductors per conduit. Cool. So detail 1. Okay, everybody knows why I went to detail 1? 1 circuit. I don't care about other circuits. I don't want detail 2 or 3. And I wanted to bury it in concrete because of safety. I don't want to bury it direct buried. Cool? Okay, so now we understand why we went to detail 1. Then 90, your option is, here, look at the option is, here's the option number 1, option number 2. Look at the voltage. My voltage is 4160. Where would the 4160 voltage be? Under this column or this column? Right? This column, 4160 is between 2001 and 500, right? So I have to go here. Can I have thumbs up, Chad? Andrew, my friend, thumbs up. Why did I go under this column here? Are you guys okay? Why did I go under this column, 4160? Why? The voltage is 4160, right? And it's within this range. If I'm doing 13.8, which column am I going to be using? This one. Okay. Now, the second option that you have to do is 90-degree column versus 105. Your default is 90-degree column unless you know otherwise. This is like 75-degree column. In medium voltage, you default to 90 unless you know otherwise. So I'm going to default to 90. And what was the current that I was looking? We forgot about the current. What was the current that we were looking for to start with? 260. So I have 260. So go under these 250, not too short. 290, perfect. So that will give me what? 4 aught. That will give me 4 aught. Can I have a thumbs up, Chad? We understand 4 aught? Okay, you guys are the best after my grandma. So this one here is going to be 4 aught. How many conductors? 3 conductors, 4 aught. And what type of insulation? I mistake number 1. We're medium voltage cables here. THW is gone. Your insulation is called MV90, medium voltage 90. Brand new insulation for medium voltage. I don't blame you for saying THW, but you go to the high voltage THW, open the window right here from the 3rd floor and throw THW out the window. THW doesn't work with higher voltage. So your voltage would be MV for medium voltage, 90 for the temperature rating of the insulation, 90.
Now, would the utility install that, or is that?
Good point.
If you are a primary user of electricity, if your service is higher than 600 volt, you will install it. If your service is lower than 600 volt, the utility will install it. Remember what we said? So probably some of you guys might never touch that in their career. You'll be the lucky ones that work with this. But yeah, if you're taking medium voltage, you'll be installing this.
Why do they do that? Risk factor, or why does it like itself default to you to install it?
It doesn't. If you're taking Excel, will decide if you're building like 3M, huge campus. They give you a voltage 13.8, and you take the voltage and distribute the voltage to all the big campus. Really, it's not that they don't trust you. You have to have qualified people to maintain it. So you have electrician qualified to work on high voltage, you give it to you. But somebody like Dunwoody, one building only, it doesn't make sense to have 13.8 here. And if you go to Excel, they will say, well, then give it to you anyway if you want to, even though it's right here next to us, 13.8. Why? The building is small in size. One building, not multiple buildings on a campus.
No, I'm saying because you said if it's over 600 volts, we're responsible for it.
If your service coming to your building is 600 volt or less, meaning Excel is giving you a 480 transformer outside on the secondary side, then you don't worry about the primary side. They bring the primary side. If your service is 13.8, meaning these cables are actually your service coming to your building here, right? Then you're responsible for installing them.
Not Excel stuff.
This question is why.
Yeah, why?
Why?
Why does Excel put it off on you?
After 600.
Right. Instead of them installing it.
This is the point of demarcation that you have to, when they give you a service, you have to decide where their responsibility start and where your responsibility ends. Theirs end and you start. So it's like demarcation cable. When you have a low voltage, right here, look at this here on the low voltage, their responsibility usually starts from the meter. If you have up to the meter, they bring cables to the meter, from the meter into your building, that's your responsibility. So it's really, they have to decide where they're going to put their responsibility, who's going to do in what.
Goes all this up to Excel.
Negotiation and Excel, yes.
They're not gonna want to pay for their trenching and the concrete.
For the 13.8 where it's going to start and stop, yeah, there's logical reasons. I mean, when they bring their 13.8 to your building, typically the first, yeah, there's a demarcation point, guys. They have to put the demarcation point somewhere. So they can put that demarcation point in a box outside or in the primary of the transformer or somewhere else. So, but for the time being, I'm assuming we are installing these and the demarcation point is right in here. That's where from here, Excel, from here, us.
Because you're talking about the 13.8 is outside the building, the 4160 is inside the building. Is that what you're saying? Or at where
Both
the
of them
service
can
starts.
be inside or outside the building.
Say it's a campus or something, and the 13.8 line comes into the property, but then you have medium voltage inside the property, and it's being stepped down in, separate areas.
Take this. Here's, for example, a 13.8 switchgear, right? This is 13.8 switchgear. So these conductors right here are my service entrance conductors. So who installed the service entrance conductor? Us, even though they're 13.8. And they land in a switchgear 13.8, right? Now, where's Excel starts? I assume Excel is bringing the cable right here. Typically what they do, guys, they have a pole here, and this power is going to be the power lines, and they have a fuse disconnect right here, and they tie their cable in here, and then from here will be tied to their system. So I don't know if you can see. So this wire, at certain point right here, and it's going to be coming down, of course, all the way and going to the building. So somewhere here, there will be the demarcation points right here at the pole that's bringing the power to your building. And again, it depends really where they want to put the demarcation point. Typically, there will be a disconnect and a fuse disconnect on the pole. The secondary side of the disconnect, that will be your demarcation point. And that's where you bring your cable up to the pole here, and Excel will tie it to their switch on the pole.
That's one way of doing it. So long story short, who's gonna install this boy here from here all the way out? Oops. Now you guys are opening a whole can of worms, but it's a good one though. So let me just say this is my pole here. And here's my power line coming in here. Let me use a different color. So I'm going to grab this one. Oops. If I'm going underground or overhead, depending. Typically, you're going underground. So coming underground here, here, coming underground, underground into here. So then you're going to have right here some type of a fuse disconnect to disconnect you from the system. That up to the red point, you install this cable up to the red point, right? Now Excel comes here and they tie this side into their power system. And this is three-phase. That makes sense? Right at the pole.
Then you install with that MV90 or whatever. it
MV,
would be.
MV90. The one that's coming right underground. This is underground.
Yeah.
Now, if you're going overhead, they use aluminum conductor serial force, ACSR, if you're going overhead. Typically, they're underground cables. So this point is here, not to interrupt you, sorry, this point here is the demarcation point. From here up, Excel own and operate. From here down, you own and operate. Make sense?
Under 600 volts, then it goes all the way to the cabinet.
Well,
Excel.
it could.
Right.
That's it. There's also a demarcation point. So, for example, if you have service overhead, the overhead service, right, they bring the voltage drop powers all the way to the service head, right? And from there, you bring your service conductor and they tie it together right at the overhead. That's that point where they tie in. That's a demarcation point. If you're coming from underground, typically you pull from the meter, you pull your conductor all the way to the pole, sometimes right in here, and the demarcation point will be right at the pole where you tie your conductors to their transformer on the pole. If you have a termination box, like we do, ours, termination box right now, to the termination box, in the termination box from the transformer to the termination box, that you put the conduit and Excel will pull their own cables. From the termination box into my building, I put the conduit and I install the conductor. So these are the arrangements that you do with the Excel. Can I move on, guys? Otherwise, we're not going to move. But good ones. Any other questions about that? The demarcation point? Good point. Very good point. Now you start to think like engineers, man. We must be doing something here. Okay. So what was the size of the conductor that we came up with? It was 3 conductors. Why 3 conductors? 4-aught, AWG, and what's the installation? MV-90. MV90. Any question, guys, about that? So that's the installation of the conductors, the installation that you're going to have. MV90. Any comments, any questions about this? You are faced with a situation like this, what do? You go to this table, you default. That's like 310.15b16. Exactly, you default. Which default? Which column? 90-degree column. Okay, so let's go back here, guys. One more time. Your default, I'm gonna say your default is a 90-degree column. But why did we go to this set of columns, not this set? Because of our voltage. The next example you're going to see, we're going to be using the second set. Okay, here's my default 2, every 4-aught. Now let's go to fuses, primary fuses. I'll get back to the fuse, guys. Let me go to the table before we do fuses. Now, number 2 is finding the fuses on the primary side. Now, is the primary or the secondary higher than 600 volt? Are the primary or the secondary? One of them, at least. Higher than 600 volt? Yes. Then this is the table that you're going to go to. 450.3a. Any comments, any question about this? That's the table that you're going to go to. Okay, how do you use this table? You're going to default to row number 1 at all times. Row number 1 will tell you transformer rated impedance, 6% or less. Are you using circuit breakers? Your default is typically fuse. Default. Can I use a circuit breaker? Yes. What's your default? I'm using the default, the most typical. As fuses. What's my multiplier? 300%. Do I have note number 1? Yes. What does it say? If it's not a standard, what do you go? Up. All right, so that's on the primary side. On the secondary side, is my voltage in the secondary over 600 volt? No, it was 480, so I have to go to this side. So my 600 volt or less. What's my multiplier, fuse or circuit breaker? 125. Do I have nut number one? Yes. So what does it mean? I go up. Any question, guys, about these defaults? These should be highlighted in your book, in your code book, guys. I know you can't read it with the handouts that I gave you, but you're supposed to take this with your code book and highlight them right there. Any comments, any questions? Any comments, any questions? So let's repeat, Jerry, my friend. On the primary, we're multiplying by 300 and going up if it's not standard. On the secondary, we're multiplying by 125, but we're going up if it's not a standard, right? Kerry, makes sense? Yes, no? Andrew? Darren, my friend? Okay. So why did I go to this table, 310.50, 450.3a? Because the primary is higher than 600 volt. I can't go to the table that we went before, the B. I can't do that. So there are two tables, 1A for if you have anything higher than 600 voltage, 1B. Okay, so let's go. So now we know what the multipliers are. And since you are my friends, we're going to go do the following. So I have, so 3 multiplied by 208, that will give me what? Give me 624 amp. And then step number 2 is to take your 624 amps and apply this one, the same default, guys, 240.6, and that will get me, go up if it's not a standard. And what's the next standard? 700. Oops, why did it do that to me? Did you do that? Where did you go?
Sleeping on the toilet, probably.
Seriously? Yeah. Wow.
Do you miss them?
Oh my God. I miss having, I don't want to have him in the summer, that's all. So,
He's gonna move in with you.
so that would be 700 amp. 700 amp. Make sense? 700 amp? Now, can I go for 600 amp? Yeah, the max is 700 amp. Okay, so that's the primary overcome protection device. The primary overcome protection device. Let's do the secondary fuse, guys. It's a secondary feeder. I want to remind you the secondary feeder, guys, is low voltage. So let's go. Any question about how we came up with the 3? Everybody knows where the 3 is. We looked at the table in a second here. 300. Let's find the secondary current. The secondary current, my friends, let's use this color. 1500K. Divide this by 1.73 times. I shouldn't do an angle. I know what the issue is. An angular. 1500K. Divide this by 1.73 times 480. If you guys do the math, you're going to end up 1806 amps. Anybody came up with something different? The ones who were working ahead of us? Okay, so that's the full load amp. Next step is I'm going to assume this is going to be continuous load, assumption, 1.25, and multiply it by 1806. That will get me a healthy 2258. 2258 amp. 2258 amps. Cool? And then the third assumption is I have my oops, I hate that, 1.5, 1.25, oops. Wow. 1.25. Okay, so I have 2258. I'm going to parallel. You guys agree with me? I can't carry this with one conductor. So I decided to use 5 sets. Can you use 6 sets? Yeah. 4 sets? Yes. What's your cutoff when you parallel? 400 amp. Try to hover around 400 amp. 400 amp, 400 kcm. That's your hover. Okay? So if I divide by 5, guys, what do you get here? You're going to get 452 amps. if you put this one through 310.15b16, what do you get? You get the following. You get 5 sets, 5 sets. Each set is going to have, now do I derate the neutral here? Secondary fuse. I want to go derate the, I didn't derate the neutral use, guys, but I really would like to derate the neutral here too. 5 sets of, excuse me, 3 conductors. Each conductor is going to be 700 kcm THH. Now, is it going to be indoor or outdoor? We're going to assume it's going to be indoor, so I'm going to do THHN, right? THHN. Why? It's a dry location. Why 3 conductors? The 3-phase. The last thing I want to do, guys, is a neutral. For the neutral, here's what I want to do. We do the same thing. You take the 225.8. The first 200, leave them alone. The second, which is 225.8 minus 200. I didn't do the math on that. Times 0.7 and add them up. Who's will be my favorite friend who does that for me? I need a second. Sixteen 41. 16, that will equal 1641 amps. Remember, you're going to add them up here. Okay? The last thing, guys, oops, we have extend page. We'll extend the page a little bit. The last thing is you take the 1641 divided by how many? 5. I didn't do that. Anybody? What's divided by 5? 3 second. 328 amps. Put this one in table 310.15b16, 75-degree column. I know that will give you 1 conductor. Remember, there's 5 sets. 5 sets of 1 conductor, 500, I think. 500 kcm, right? 400. So am I lying to you then? 400. Okay, oops. Should have waited until you give me the answer. Thought I'm smart aleck to get it. 400. So 5 sets. 5 sets. 5 sets. Cool. Any question, guys, about this? So we calculated the neutral. 5 sets. Okay, let's go to the overcam protection device. The overcam protection device, fuse. So overcam protection device, guys, we did the same calculation as you remember. Secondary overcam protection device, 1.25. Multiply that baby by 1806. That will give you a healthy 2258 amps. I don't know if you guys came up with this, 2258. You take the 2258, the next step, amps, 240.6, your next standard is 2500 amps, and you go up if it's not a standard. Any question, guys? So 2500 amp on the secondary side. 2500 amp on the secondary side. Fuse or circuit breaker, we don't care. It's secondary, same sizing. Okay, grounding electrode conductor. Grounding electrode conductor, guys, since we have 5 sets, here's what you need to do. You need, since I'm paralleling 5 sets, you take 5, multiply it by 700 kcm, you end up with 35,000 or 10, 3,500, right? So that's what you end up with, 3,500 kcm. step one. Step two, you take the 3500 kcm, take it to which table? Table 250.66, and that will get you a healthy, how many conductors? One conductor, 3 aught, AWG, TH, HN, or bare, or insulated, or or covered, right? Piece of cake, really piece of cake. The last thing on this, okay, so the last thing, let me know when you guys are ready. Cool? Oops, sorry. I'll go back. Right? So now the system bonding jumper, for the system bonding jumper, guys, you're gonna do the same thing. You're gonna take 5 times 700 kcm. You're gonna end up with 7,500 kcm. The next step, you're gonna ask yourself, is 705 kcm, is it more than 1100?
It's too much, Jeff. How did you get?
It'd be 3,500 KCM.
35.
I didn't write 75, did I?
Your grandma did.
It's not there, see? I didn't write it. Good thing that we're recording here. Otherwise you don't have a record of that. Wait till get this, everybody. Okay, let's go here. So 5 times 700 kcm, that will give me 3500, right? kcm. Step 1. Step 2. So that's my step 1. My step 2 is to 3500 kcm. Is it more than 11 kcm? Is it more than 1100 kcm? Your answer is what? Yes. So what do? You go to step number 3, which you take 12.5% and multiply this by 3500K, right? Everybody knows what we did, and then you end up with 438 kcm. Now, unless you are my friend Jamie here, and you can afford to buy 438 kcm, if you're like the rest of us, you're going to go find the next standard. So how do you find the next standard? The next standard, my friends, will be to take the 438 kcm. Where do you guys? Chapter 9, and you see table 8. Table number 8, and that will get you, oh, no problem, one conductor 500 kcm. I don't think we have 450, do we? We have 350, not 450. So the size would be one conductor. What insulation? THHN or bare? Typically insulated or covered at least. Okay, so the last thing I want to show you guys right here, and so here's the 5 conduits you're looking at. Now the conductors will be 3 conductors, number 500 kcm, and the neutral conductor, we screwed up here. The neutral conductor would be one conductor. What was the size of the neutral that we came up with? 3 aught. 3 aught. AWG. Are you sure it's 3 aught?
No, 400 KC.
How much?
400 KC.
Thank you. That sounds small. So one conductor, 400. What did you say, Kerry? 400. 400 kcm. Can you see, guys? So here's your 3 conductors, the 3 phase. and a neutral. Any comments, any questions? Any comments, any questions? Okay, I'm gonna give you guys 5 minutes and I have to do one more example and then we'll let you go. Yes, sir.
The 600 mil area only goes up to 211 KCM.
Flip to the other side, to the column one. Then the same table, column one, same table. No, go back. Yeah, the first column.
Yeah.
Yeah, the first column becomes the KCM. After 4 aught, they start sizing him in KCM. Make sense? Yeah, they start sizing him in KCM. You can't believe how many times I get asked this question, Aaron, is you're not alone. Chad, 500 KCM doesn't have how many KCMs in it. It's because it's in a KCM. No problem. Okay, so let's go, guys. And start, and we can go. Okay. All right, so come over here. Okay, so here's the system that we have. Here's the system that we have. I have a 13.8 volt system, primary, feeding a secondary 4160. Can you guys see that both the voltages on both the primary and the secondary are higher than 600 volt? So that's, can you use 310.15 B16? Nope, not anymore. The transformer atom is 10 megavolt amp, big boy, 10 megavolt amp. Okay, and we're supposed to do the following. We're supposed to, it's both of them are delta delta. This is typical for these. We don't have a Y. Why do you think we don't care about the Y at 4160? Anybody? I mean, 4160 for commercial building, guys, industrial building, they don't use line to neutral on high voltage. They always use 3-phase. Like, for example, North Star Steel, they have equipment that they burn their motors at 4160. They tie the motor directly to 4160. So 4160, there's a lot of equipment that work at 4160. Okay, so, but the neutral is not needed. Okay, in a case like this, because the neutral is not needed, the only thing you need to provide here is grounding electrode system. You still need to provide a grounding electrode system. Where is the bonding jumper, Chad? Where's the bonding jumper here? No main bonding jumper because I don't have a grounded system. This is an ungrounded system. Can I have thumbs up that we understand why we don't have a main bonding jumper here? Because this system does not need a neutral. Okay? So I'm only pulling 4160. The same thing, we need to size the primary conductors and fuses, the secondary conductors and fuses, and the grounding electrode conductor. The only thing that we're missing is the main bonding jumper because it's not needed because the system is ungrounded system. This is called ungrounded system. Do you see any windings connected to the ground?
So are you attaching the ground to like the transformer itself?
Yes, the frame. That ground here, the ground bar, is just grounding the frame of the transformer and the conduits. But do you see the windings themselves? The wires, any wire connected to the ground? No. The conduits and the frame, the box. Every system have to have equivalent ground conductor, guys. But is the system grounded or not? 90% of system are grounded, but there's 10% are not. This is one of them. Okay, let's go ahead and do the calculation for the primary conductor, exactly like you have done. So I'm going to speed up on this. I have a 10. This is a 10, 0, 0, 0. That's another 0, 0, 0, right? That's a 10 million volt amp. 10 mega amp is 10 million volt amp. Divide this by 1.73 times what's the primary voltage? 13.8. Since we're doing it this way, so let's say 0, 0, right? So 13,800. So I'm just putting the zeros all together here because there's so many zeros. So if you do your math on that, 13.8, you're going to end up with 419 amp, 419 amps. We've just started, Aaron, my friend. 419 amps. That's what you came up with, right? 419 amps. Cool. Okay, so that's the first thing you need to do. The second thing is we're going to assume This is continuous load, and we're going to size it based on 1.25. 1.25 times this one by 419 equal, that will give me, where does it get me, Chad? That will give me 524. 524 amps, okay? 524 amps. Then the last thing you need to do is you need to take the 524 amps, take it to where? This is the table that we were just looking at. Table 310.60C77. 77 under 90-degree column Celsius. When you go there, which is I think the next step, right here. There you go. So if you go, we're looking at, here's the table that we go to. Why do you think I went to this side? Because I have 13.8K. My system is 13.8. Everybody knows why I went to this side? 13.8. Here's my medium voltage 90, and I'm looking 524 amps. 524 amps. That will give me 564. So would that give me number 750? Everybody can see that? You got 750 right in here, right in here. 750. Cool. Why did I go to this column? Always go to the 90. Why this set of columns, not this one? Because the voltage is 13.8 and it lies right in here, not here. Cool. Can I have thumbs up, Shall we fully understand that? Cool. So based on these tables, then my conductor is going to be 3 conductors. I'm going to move this one up a little bit here. So I'm going to have 3 conductors. Oops, that sounds like a coil, not a 3. So I'm looking at 3 conductors number 750 kcm. What's the insulation though? MV-90. This is the proper answer for this boy. Cool. And do you guys remember how the ducts? How did we put them in? What type of a duct that we put them in? We put them in. We put them in one duct, right? One duct, one circuit, one duct. Can I have thumbs up, Chad? We fully understand. Detail 1 is one duct, one circuit. Cool. You guys the best after my grandma. Okay, so that's what you get. That's what you get out of this. Any comments, any questions? These are the conductors, the primary conductors. Piece of cake. Piece of cake. So when you go down here, this is, we'll get into the fuses. So this is how your primary conductor detail 1, right? And 3 conductors, and the size of these conductors are going to be 3 conductors. Here's detail 1, and you see all this information. You guys are 310.60 C77, 3 conductors in 1 duct, 11.5, 11.5 encased in concrete, buried with 24 inches underground. 24 inches underground. Come on, does that make sense? The duct that you put? Okay, let's go to the fuse. So let's go to the fuse. Now fuses, let's go back to the fuses. You guys remember the fuses? I have to use this table because both of them are high voltage. I remember we're going to use to any location, not more than 6, my default, and I'm using a fuse. So what's my multiplier? On the primary side, 3. On the secondary side, I'm also over 600 volt, and I'm using also fuses. What's my multiplier? 250. Can you guys see that's the secondary side, the primary side? So we're doing the primary. Let's focus on the primary. The primary, everybody knows why I'm using a fuse. I decided to use fuse. And I'm using 300. Do I see note number 1? Yes. So what do I do? Go up if it's not standard. So what's my multiplier? 3. 300. Okay, so having said that, here's what you're going to do. So you have your primary conductors, my friend. Where am I here? So you're going to have 3. So you're going to have 3 times, what was the current that came out of this one? 419. And that will get you a healthy 1257 amps. You take this one to 240.6 and that will get you a healthy 1600 amp fuse. So how many fuses? 3. Why 3? 3 phase. What size of fuse? 1600 amp. What's the voltage of these fuses? the voltage will be, it has to handle 13.8. The next standard fuses, guys, they call them 15K. It's a 15K rated. There's 600 volt, and there's 5K kilovolt rated fuses, and then 15, then 25, then 35. They start rating based on voltage. This one will be 600 amp fuse rated for 15 kVA, which can handle the 13.8 that we have. Piece of cake. Any comments, any questions? Any comments, any questions? Anybody's excited? No? No? Okay. It's not Friday, it's not Monday, so what is it today?
Monday. It's not Friday, it's Monday.
Okay. Any question about the primary, guys? That's it. We sized the fuse and the circuit breaker for the primary side. Now let's go to the secondary side. On the secondary side, Adam, my friend, I will use the same 10 meg, 10, 0, 0, 0, 0, 0, 0. Divide this by 1.73 times, what's the voltage on the primary? 4160. 4160. And what's my, if you guys do the math, what's my secondary? I have 1390 amp. 1,390 amps. Anybody came up with something different? 1389?
12.5.
Close enough for government work. Okay. Does that make sense? Jeff? Makes sense? Okay. So let's go to, I'm going to spend more time on the important stuff. Let's go down to and do the calculation now. Now, you guys agree when I came up with 1390. Can you find a conductor that can carry 1390 amps? They don't make them. So what do you need to do? Parallel. Now we're paralleling medium voltage.
You have to multiply that by continuous load.
Before we multiply. So the first thing we need to do, thank you, is we want to take 1.25 and slam it by the 1390, and that will give me 1738 amps, if I did my math right. Now this multiplier, guys, at this voltage, some people might not put it even there, 1.25, but it's a good practice to add 25%, assuming it's continuous load on the feeder. Then we're going to parallel. So I have my parallel. So I have 1738 divided by how many of them? 6. I'm going to divide it by 6. 6 of them. Could I have done 5? Yep. 6 of them. 6 will give me 290 amp. 290 amp. Then the third step is you take the 290 amp. Take it to 310.60 C7 9 detail 3. Look at the detail. Detail 3. I'm going to tell you why we guys use why I use 6. Everybody knows why I use 6 here? Because I have a detail for 6. Everybody can see that? Why didn't I use other than 6? I have a detail for 1 circuit, 3 circuits, and 6 circuits. So if you parallel other than these, you're on your own. You have to do calculation based on engineering softwares. We don't have them, so that's why I picked up 6. Everybody can see why I picked up 6 here? Because we have 6 circuits in 1 ducts underground installed. Thumbs up, Chad? You understand? We have 6 circuits here. Okay, let's go back. So here's my 6 circuits that we did. What size though? I came up with 3 conductors. Each one of these boys is number 500 KCM and MV90. Okay? 6 sets. Thank you. 6 sets. You are the best. There you go. 6 sets. 6 sets. You always have to put how many sets, right? You guys you must be listening to me. Okay. All right, 6 sets of 3 conductors. There you go. 6 sets of 3 conductors, 500 kcm each. 500 kcm each conductor. medium voltage. Okay, so this is how it's going to look like. It's going to look like a concrete encased ducts like this, PVC or concrete ducts that they make. You put three phases in one duct. They look like this: phase A, phase B, phase C, A, B, C. And when you tie them, the way they look at the end, guys, when they parallel them, here's phase A, here's conductor 1, 2, 3, 4, 5, 6 conductors for phase A. So phase A will have 6 conductors tied from both ends. Everybody understand? So they will take phase A from here, 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 and here, and tie them to one set of lugs at this end and another set of lugs at the other end. Does that make sense?
Okay, where are you looking at?
Are we doing a different table?
It's C77, isn't it?
Yes. So let's go to C77 here.
Would it be,
Hold your horses.
4 out there?
Let's go to C77. For C77, we're going to use detail. Yeah, we use, hold your hands. We're going to use detail, I use a different detail. Oops. I'm glad one of us is awake. We're going to use the detail, detail 6. So give me 1 second here. Bam, 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 Chad. Let's,
I see where it is.
did we use the right detail though?
I didn't look down farther down.
Did we use the right detail though? I don't have a picture of it, but did we use the right detail? 310.60. I think we did the right detail. Where the heck did it go? 310. 310. Here you go. Right here. Okay, so 310.77, right? Is that 77 the one that we do? Okay, 87, all the way here, 83, 81, there you go, 79, 77. Here you go. Can you guys see 310.6077? I'm going to go all the way to detail 3. Everybody can see detail 3 right here? Okay, so here's detail 3. Why detail 3? Everybody see why we use detail 3. So the voltage was, what was the voltage again? 4160, right? So that will be here. The voltage was 6 ducts, detail 3. The voltage was 4160 volt. And what was the amp again? 290. So I'm going to go under the column 90 degree 290, 290, 29. So that will give me here, right? And that will give me 500. Everybody can see where the 500 came to be?
Yep.
Everybody see where the 500 came to be? I didn't just take a snapshot of that. Where's my snapshot so I can get my snapshot? Okay. Let me take a snapshot of it so I don't forget. If you guys don't mind me taking a snapshot. Okay, where am I here? Here. Okay. Let's use the whole deal here. Okay. So this is where we got our 13.8. This is where we got the 500 kcm. Okay. Secondary conductors. Any question, guys? So this is where we got the 500. Does it make sense? Makes sense. Okay, let's go next. So here's the detail. Oh, actually, I have it here. No, that's detail 1. Okay, 6 ducts. Yeah, here, I actually have it here. I just didn't go fast enough. You guys should have looked at mine.
Said 379 for the table.
379?
Well, one of them said.
It should be, okay, so the table that we use for this one's the same table. 370,
So,
yeah. And I'm using 379. 3 insulated conductors, cable. 1 second, let me just see which table. I don't use them often. Okay, 379 ampacity. They're just the type of the ampacity for them. Okay, give me 1 second here. Sort out this boy. $379, $379. Okay, 3 insulated cover conductor cabled with an overall covering. Yeah, you know what the difference, guys, is this? These are 3 cables in one, 3 conductors in one cable, or 3 single conductors. The 79 give you 3 conductors in one cable. Let's use 377, will you? 3 conductors separate, 3 conductor cables. Okay, where did I say that as I'm using it? So I can correct it. 379. Let's use the 379, 75. I'll delete that one. Okay, let's use the 370 right there, here. That one. 500, right? Everybody got the 500? So let's ignore the 379. I'm going to go down here. Can you guys change this one to 377, please? Change it, please, to 377. Stay in the same. It's stay in the same table. Could I have used 379? Yes. Yes. It's just multi-conductor cable versus single conductor cable. Okay. Multi-conductor cable versus single conductor cable. The problem that I'm showing, guys, I'm showing right here. The problem is I'm showing cables here. Can you guys see showing cables here? So why don't you, lie to you again, let's make it 79 just because my diagram, guys, shows a cable here. Can you guys see a cable? My diagram showed a cable. Let's just use a cable. Enough, a different way. Just because my diagram is showing a cable, multi-conductor cable. I don't want to redraw the cable. I'm just lazy.
And size-wise, they're the same thing.
Yeah, same in terms of size, the same way. It happened to be the same way. Don't have to be. Okay. So I don't confuse you and confuse myself. I'm going to go delete this section here. And okay, we get that one. Okay, now for fuses, you guys remember what the fuse on the primary? It's going to be 2.5, right? 2.5. So let's go size the fuse. So we size this. We get that one, got that one. Okay, so let's go size secondary overcome protection device. For secondary overcome protection device, my friends, right away, I have the 100, my secondary overcome protection device. What was the multiplier for the secondary, guys? 2.5. So I have 2.5. 2.5 times, what was the full load current of mine? 1390. What do you get? You get 3475 amps, right? The next step is to take this boy, 3475 amps, take this one to 204.6, and I hate to go there, but I have to, and that'll get you a 400 amp. 400 amp times 10. Trying to be smart, Alec, huh? 4,000 amp. Thank you. That'll get you a 4,000 amp. That'll get you a 4,000 amp. The last thing I'm going to size, guys, for this boy is the grounding electrode conductor. The grounding electrode conductor, that will be 250.66. The high voltage section. And that will be 6 times 500 equal 3000, right? KCM. Why did they put the comma here? I don't know. So that will be 3000, right? 3,000. 3,000. Okay, then you take the 3,000 KCM to 250.66. What do you get? One conductor, 3 aught. Now this one can be THHN. It's a grounding conductor. Typically they are THHN conductor. They don't have to be medium voltage. They don't have to be medium voltage. The reference for this one, my friend, is grounding electrode conductor, high voltage system, higher than 600 volts.
No.
Okay, 250.190. Can you guys put the reference here? Um, Actually, your reference here is 250.190. 250.190. That's the high voltage reference, 250.190. Okay? And which actually refers you to 250 to table, it refers you to table 250.66 anyway. But just a reference. Okay, let me move into one very important, guys, and then I promise I'll let you go. Any comments, any question about this? See how easy and nice and easy breezy? See, you guys continued that. The last thing I added here, guys, is the short circuit rating. Short circuit rating. This is really good to know. Short circuit rating for the transformers is on the secondary side. On the secondary side. So to find the short circuit rating, you need the secondary conductor and the impedance of the conductor. Piece of cake. What was the secondary, not conductor, secondary current? The secondary current, my friends, we just find it 1390. Divide this by Z. Z is the impedance, or Z. Is it Z or Z? Z. Not Z? So Z, I grew up calling it Z. Z 1390 divided by Z. Z is the impedance on the nameplate. You don't know the Z, so you have to get it from the manufacturer. I'm giving you as 6%. Z is 6%, so 0.06. If you guys do the math on that boy, you're going to end up, you do the math, you're going to end up right here with 23.2 kiloamps. You do the math, 23.2 thousand amps. So here's what the primary, this is how it looks like. Here's your primary of the transformer, right? This is tying to the transformer. From this side, this is the 4,400 amp fuse. I'm showing you a fuse, guys. Here a fuse, 400 amp fuse. One side tied to the transformer. The other side is tied to all these 6 sets of 500 kCl. Does that make sense? With special lugs. This fuse has to be rated for, look at this. It's 23.2 kiloamps, so this has to handle 23. The next standard typically is in multiples of 5, so that will be what? 25. And what's the voltage rating of this secondary of the transformer? It was 4160. The secondary here, guys, the secondary is 4160 volt. So that when I buy a fuse, I buy a 5 kV fuse rated for 25,000 amp interruption and full load amp of 400 amp. 4,000 amp. Any comments, any questions, guys, about this diagram? Any comments, any question about this diagram? That's the transformer secondary, the fuse, and I know I'm not showing a disconnect here, and the conductors that tie to it. The fuse will be 4,000 amp, interrupting rating 25K, and voltage rating is 5K. Okay? Now I'm going to use one last example, and I'll let you guys go, my friends.
I thought the last one was the last one.
Yeah, you said you're gonna let it go
The last one was the last one. This one is really good. You guys need 5 minutes? Stretch a little bit. I know it's too much, but I really want to finish this one. Let's take 5 minutes, because I need your full undivided attention for that one. Thanks. Do me a favor. This example is very important, guys. So do me a little favor here, just a little favor. I promise it's not going to go long. Okay, this is very important. I want you to look right at the bottom here. Every building that we have is going to end up having a transformer that feeds a receptacle panel. Every single building that you're going to encounter. The building that we have right now for our project 28120 doesn't need a transformer receptacle panel transformer. Why? Because the whole service is 28120. Almost 80% of the building that you're going to encounter is going to have a 480 panel that feeds a receptacle transformer that feeds a receptacle panel. How many of you guys have seen that? All the time. So let's see how we can size the system. Do you guys understand what this is? This is a special system, a panel transformer a 480 panel feeding a receptacle transformer that feeds a receptacle panel. Can I have thumbs up, Chad? Cool. Two things. Now, when you do size the panel, do you guys remember how we size the receptacle panel? You take the kVA of all the receptacles, and anything higher than 10,000 volts, you cut them by half, add them up, you derate them. And you come with a big chunk of kilovolt amp. Can I get you guys, we come up with a big chunk of kilovolt amp. So suppose when I sized this panel, suppose I came up with 72, like when I did the calc on that one, I came up with 72 kVA. I came up with the size of 72 kVA. The first thing you do when you come up with the kVA size of the panel, you guys came in, right? You came up with the size of kVA of a panel, right? The first thing you do is go find a transformer that can get you this size. So can you guys go with me to DeWalt 7-7, DeWalt 7-7, you have the ones who have DeWalt 7-7, and find me a transformer that can carry this panel. 7-7. How many of you guys are there? 7-7. Am I the slowest kid in the town here? Okay, if you guys go there, 7-7. If you look at the 7-7, yep. If you look at three phase, there are three phase. I want to look at 2.8. So what size transformer can I get? Look at the first column, and look at my derated receptacle size is 72. What's my next standard? 75. Do you understand why I came up with 75 kVA transformer? Everybody understand now? I did the calculation on the receptacle panel. I came up with 72. My next standard is what? 75. Can I have thumbs up? We understand? Now, if you understand, suppose that the load that I calculated for the receptacle panel was 23. Can you size the transformer to feed a 23? From there, what's your next standard? 23? 30. Everybody understand that? Cool. That's the key point. Okay, so I have my receptacle panel, and I found that 75 can feed it, right? It gives it more because it's more than 72. Then what do I need then? I need to tie size conductors between the receptacle panel and the transformer, and also the overcome protection device ahead of the panel, and also the overcome protection device on the primary side. So I need to size the conductor on the primary side and the overcome protection device, the conductor on the secondary side and the overcome protection device. Typically, guys, they have I have a distance. D stands for distance. The distance between the panel, the receptacle panel, and the main panel is 25 feet or less. And I'm going to ask you ignore this for a second. But typically they are in the same room, the receptacle panel here, and the transformer on the ground, and the lighting panel, the 480 panels here, 280 panel here, transformer right in between them. Okay, so they are within 25 feet of each other. It's going to come very handy in a second here. Okay, if they are within 25 feet of each other, then I don't need a secondary fuse here. Can you guys see that? There is no fuse needed here. And the secondary protection will be right inside the panel. Did you hear me? If they are within 25 feet of each other, then you don't need a fuse right by the secondary to protect the secondary. And you can size the overcome protection device inside the panel will act as the protection for the panel and the protection for the secondary of the conductors. So 2 birds in 1 stone. Can I have thumbs up, Chad? Cool. Okay, so let's go ahead and size. So the first thing you need to do, take the 75 like we have just done, 75K divided by, by the way, I'm doing the secondary first. I call this as receptacle panel size. I want to find the receptacle panel size. Take the secondary current of the conductors, so 1.73 times, what's the voltage in the secondary? It's a 28120, right? Everybody knows that the secondary is 28120. Do we have it here? Yep, 28120. 208. So what's the full load amp? Anybody came up with a number? 208 amp. So the full load current of this transformer is 208 amp. Right? Anybody came up with something different? Okay, now, because we have a panel tied to at the end of it, not a load, a panel, here's what I would do. I would take the 208 amp and take it directly to DeWalt 3-12 and find a panel size. I want to tie a panel at the end of it. If you guys go there, 3-12, panel size, three phase, remember, everything three phase, what do you come up with? 225, thank you. 225 amp. So what size panel am I going to be installing at the end of this transformer? 225 amp panel, 208, 120, receptacle panel. Can you have thumbs up, Chad? So we, from the full load current of the transformer, now some people guys take this one multiplied by 1.25 because of continuous load and because of future. I want you to understand, remember we went from 72 to 75, so there is extra load. So if you go, and there's also, we went from 208 to 25, there's also extra amps here accounted for. So based on the full load of the transformer, size of panel. Can I have thumbs up? Cool. Next, overcome protection device. Now you need to size the overcome protection device. Same thing. You take the 208 amps of the secondary, take it to 240.6. What's your next standard overcome protection device? 225 amp panel. So we hit the jackpot, right? We match the panel to the overcome protection device. It doesn't have to be. You could end up with 100, say 200 overcome protection device. In this case, both of them are the same size, so we're cool, right? So I size the panel, and I size the overcome protection device that's going to sit inside this panel at the main. Does that make sense, guys? Right, that here. Do I need another fuse or circuit breaker right here? No. Why? Because they are within 25 feet of each other. They call it the tab rules. You're going to see in a second, the tab rules. Can I have thumbs up that we got that one? Cool. Let's go to the next. Next. Now I need to size the secondary conductor or the receptacle panel feeder. Does that make sense? The secondary conductor of the transformer are the feeder of the receptacle panel. Can you guys see that? Everybody can see that? If you go here, the secondary conductors right here are actually the feeder of the panel. So it's the same feeder, okay? So we're going to size that one. So let's go there, size it. How do we size it? Match overcome protection device. Always, because it's a panel. So I have 225 amp, 225 amp panel. 310/16B, 310/15B, 1675. That will give me a size of, now, remember, I'm not far away from the 200. So in this case, up to probably 200, up to 300 amp full neutral. After that, you start derating neutral. In this case, because it's a smaller panel, 225 amp, I don't want to derate the neutral. You shouldn't derate the neutral there. So how many conductors? 4 conductors. What size? Number 4 at AWG THHN. THHN. Make sense? Does that make sense? Piece of cake. Now we size the cable between the transformer. We size the cable, guys, between the transformer and the panel. Between the transformer and the panel. That's it. Should I multiply by 1.25? Some people do. It's not a good idea. We already derated. If you do it, is it bad? No. Okay, so that's the secondary side. Let's do the primary. For the primary, guys, the same thing. You would take the 75K divided by 1.73 times 480, and you would end up with 90 amps. 90 amps. Now, I have people who take the 90 amps multiplied by 1.25 like we have just done. You can do that, but since I know what the load on the panel and the load on the panel is already known, I think you don't need to multiply by 1.25. If I multiply this by 1.25, would it be wrong? No. So, but because the receptacle panel is already sized, and I'm sizing it to match the panel, so I'm not going to exceed the panel rating anyway, right? I'm not going to exceed the panel rating. So what I would do is I would size this one directly based on 90 amps. So 90 amps, no multiplication, 1.25, and you would end up with 3 conductors, number 3 AWG THHN. If I give you a panel, that's how you do it. if I don't give you a panel, if that was just a transformer and landing on an equipment, you multiply this by 1.25. Because we don't know what the load on that. It could be continuous load. A panel, I already assigned a 225 amp circuit breaker ahead of the panel. I can't pull more than 225 even if I want to, because it will trip, right? So I'm limited to 225 amp. My cable on the primary and the secondary match the 225. So I'm good to go. Okay, so the controversy is, do I need to multiply by 1.25 or not? If you do, it's good. I think you should, there's no need to it. Okay, the last thing, guys, is the primary overcome protection device. Now remember, the primary is 480, and I think it's, if you go to 480, the multiplier for 480, right here, if you go to 480, the multiplier for the primary is what? 250, right? Can I go up? No. So 250, so here's what I would use. I would use 2.5 times 90. I get 225 amp. Take this one to 240.6, and that will get you again 225 amp. And if it's not a standard, what do you need to do? We have to go down. We end up hitting a standard 225 amp panel. Now here's my question for Jeff and Darren. If you went and you put a 200 amp on the primary, is it wrong? No. If you put 150 on the primary, is it wrong? No. What's the chances that you're taking? The chances that you're taking is you will trip the primary circuit breaker when you energize the transformer. Now, if you have done it before with certain transformers like you guys at Egan, you would do it all the time, and we know that 75 circuit breaker, 75 amp, 75 kVA transformer, on the primary, we can put 100 amp on it or 150, and that's good protection for it based on the size of the transformer and the type and the manufacturer. Is there anything wrong with that? No, that's the max. I can't emphasize this one because I don't want you to go to work and you see people putting a 200 amp on it or 150 and say, what the heck is Chad talking about? That's the max. Cool? All right, so we're almost there. So that's my primary overcome protection device. So we size the overcome protection device primary. Now, the last thing I want to tell you guys, that we're done. We really sized everything we want. Everything that we need is sized. Let me go back here. And so we sized, here's my panel, 225 amp panel, 225 amp circuit breaker, number 4 arc conductors, the fuses here were 225 amp fuses with circuit breakers, the conductor were number 3, and we're good to go, right? We're done. Now, the check that I want you guys to do is, because there is no secondary protection here, is there any secondary protection here? Right here, and I put my secondary protection right in here. They call this is the tab rule for transformers. Tab rule number 20, tab rule 25 feet or less. Tab rule 25 feet. So let me tell you the tab rule 25 feet. It's right in here. We'll talk about tab rules. Here's the tab rule that I'm talking about, directly from the code. It says tab supply transformers, primary plus secondary conductors, 25 feet or less. Everybody can see that? That's the rule that I'm said from the code. Anyway, to summarize all this, if you read this, I want to summarize it in one slide. I'm just going to prove to you that what we did is right. That's all. We're done sizing. Based on the tab rules, you're going to do the following. You're going to do the following right here. Okay, here's what the tab rule says. The tab rule, guys, says, see what's conductor number 1 here, C1 and C2. It says C1 conductor must be more or equal to 1/3 of the overcome protection device, or you cannot do this. So look at this, C1 tab rule. C1, that C1 is here. The conductor must be more or equal to 1/3 of the overcome protection device. So let's go do that. What's the number 3 conductor can give me 100 amp. I already used number 3 here. 100 amp. Is 100 amp more or equal to 1/3 of 225? Because my overcome protection device is 225. If that's true, then I'm good. So here you go. What's 1/3? 75. Is 100 amp more than 75 amp? Yes. So is my design good? Yes, based on the tab rules. Can I have thumbs up, Chad? See how easy that? They say the conductor that you tap from the primary here the tap conductor here cannot be less than 1/3 of the overcompression device. Okay, that's C1. This is this conductor. On the secondary side, guys, on the secondary side, C2, that's what's confusing. It has to be more or equal to the ratio of the voltage multiplied by 1/3 of the overcompression device on the primary. Okay, let's go do that. So what's the conduct? I have 4 aught. 4 aught can give me 230 amps, right? It's more or equal to, you take the 480 divided by 2.8, multiply it by 1/3, multiply it by 225. You do all this math, you're going to end up with 173 amps. Is 230 more than 173 amps? Yes. Are we good design? Yes. Done. This slide is FYI only. We've just done the design. Okay? Any questions, any comments? Any questions, any comments? So this is just to get you, when you do the tabs, the 25-foot rule tab, you have to make sure that this conductor on the secondary cannot be less than 1/3 of the overcompression device on the primary. On the secondary, it cannot be less than 1/3 of the primary overcompression device multiplied by the voltage ratio. The voltage ratio. Primary to secondary. If I put you to sleep, that's probably the intention here. Okay, and here's the rule, guys. You can read these rules. Conductors in the secondary, not less. All the stuff that I summarize is right in here. I will visit, Andrew, the tab rules. If you guys are still with me in the spring when we do the commercial, we will visit the tab rules a little bit more. But for the time being, that's just little introduction to the tab rules. Okay? That's all I have for you. Any questions, any comments, my friends? Any questions, any comments? The only thing I want to emphasize without getting into the details, I want you guys to be able to size this system, right? That's it. Thumbs up, thumbs down in between, 75-degree angle. All right. Okay, so that's the first introduction to the panels and the transformers and so forth. Okay, thank you guys.